The following is a high-level comparison of X-ray detector systems used in modern digital radiography. All have significant advantages to film radiography, but each produces its image in a different way. Presented are the basic mechanics as well as the pros and cons of CCD, CR, direct DR, and indirect DR systems. For CCD systems, X-ray photons pass from the generator through the patient, and those that are not absorbed by the patient are incident on the layer of scintillator material, which converts them to visible, in most cases, green light. This green light that emanates from the scintillator layer is focused by a lens onto a CCD camera, which converts the light to an electrical signal, which is electrons, that can be read and processed by a computer to yield an image. An advantage of CCD systems is its speed. The CCD array, CCD stands for Charge Coupled Device, much like the ones used in digital cameras, transfers its signal for processing very quickly. Also, in very tight collimation, that is when photons pass close to the center of the lens, the image quality is very good. And being relatively older technology, the price point of these systems makes it very affordable. There are, however, several disadvantages of this system. Compared to the flat panel detectors that follow, the form factor of CCD systems are quite large, making them less convenient. Also, when the collimation is wider so that the light passes closer to the outer edge of the lens, there will be a distortion along edges of the image. This comes from using a spherical lens to focus light onto a flat surface. And you may have seen pictures of square grids imaged on CCD systems that appear to have curved lines along the edges. Also, because there needs to be space between the scintillator layer and the lens, and between the lens and the CCD, the light has room to spread out, and so actual resolution is significantly lower than the spec resolution of the CCD. These separation distances also lead to a background glare where light from the X-rays that struck the scintillator outside the shadow of the patient get focused on a part of the CCD that is inside the shadow of the patient's image, thereby creating a glowing image. Finally, this is older technology, and often the different components, like the scintillator, the lens, and the CCD, are manufactured and supported by different companies, making servicing these systems a challenge. The principal manufacturers of CCD systems that are still available in the veterinary space are Hudson Digital, Sedical VetRay, ClearVet, and Naomi, with an average price of $20,000 and then $40,000 if you include a table. For computed radiography, or CR detectors, X-ray photons pass from the generator through the patient, and those that are not absorbed by the patient are incident on a layer of material with photostimulable storage phosphors, which convert them into electrons and stores these electrons. To get an image, the cartridge that contains this material is placed into a digital scanner, where a laser beam scans the entire exposed area. As the laser beam passes through a region of the material, the stored electrons are released and read by a computer, which then processes the signal into an image. An advantage of CR systems is the image quality, which is generally comparable to other digital modalities. Also, being very relatively lower priced system, the quality for the money is very good. There are, however, several disadvantages of these CR systems. The two-step process, that is first exposing the patient, then carrying the detector to the scanner to be acquired, is reminiscent of film. It eliminates the potential to take multiple views sequentially and presents a significant workflow inconvenience for the radiography staff. Also, the resolution achieved is dependent on the speed of the scanner. The faster the scanner progresses through the cartridge, the more blur appears in the final image. So while current models have increased their acquisition speed, they still fall well behind the digital flat panel detectors to follow. The principal manufacturers of CR systems that are still available in the veterinary space are Agfa, Fuji, FireCR, ScanX, and Konica Minolta, with an average price between $10,000 and $20,000. For direct DR detectors, X-ray photons pass from the generator through the patient, and those that are not absorbed by the patient are incident on a photoconductor layer, which is usually made of selenium. This directly converts them into electrons that are subsequently processed by a computer into an image. Advantages of these direct DR systems, as distinct from the indirect DR systems to follow, are the speed of the acquisition and quality of images. Also, being a fully digital process and containing a flat panel architecture, these systems are very convenient. There are, however, several disadvantages of these systems. The photoconductors do not absorb X-rays as efficiently as scintillators. This means that for a given exposure dose of X-rays, the acquired signal is lower, the noise is proportionally higher, and therefore the image quality, which is directly related to the signal-to-noise ratio, is diminished. This effect is especially present in the low-dose areas, like beneath large anatomies, limiting the overall functionality of the system. To compensate the technique, either the amount or energy of the X-rays must be increased, but this has two non-trivial implications. First, the radiation exposure to the animal as well as the staff is increased, which presents its own problems. And second, since the electronics are closer to the exposed surface of the detector, radiation exposure to these electronics is higher, and therefore radiation damage is more likely, and the lifetime of the panel may be diminished. For these reasons, this technology does not appear as mainstream in the human or industrial imaging industries. The distributors of these direct DR systems in the veterinary space are IDEX and Patterson. The average price for these systems is about $40,000. For indirect DR systems, X-ray photons pass from the generator through a patient, and those that are not absorbed by the patient are incident on a layer of scintillator material, which converts them into visible, in most cases green light. This green light that emanates from the scintillator layer is read by an array of photodiodes that convert them to electrons. These electrons then activate a layer of amorphous silicon that is imprinted with an array of TFTs, or thin film transistors, that make up individual pixels, which capture the electrical signal, which is electrons, and can read and be processed by a computer to yield an image. These indirect DR systems are the gold standard of the medical imaging because of their combination of speed, high X-ray sensitivity, and low noise that lead to excellent image quality in a compact, fully digital architecture. If there are pitfalls in this system, one would be the slight resolution limit due to the potential lateral spread of the light and electrons in the sub-millimeter thickness of the detector. Also, since each conversion step from X-rays to light and from light to electrons has less than 100% efficiency, the overall conversion efficiency can be suspect. But over the years, manufacturers have improved their materials and construction to minimize these factors to virtually negligible levels. The principal manufacturers of indirect DR systems that are still available in the veterinary space are Varian, Canon, Rayance, PerkinElmer, Samsung, Fuji, Vivex, Toshiba, with prices ranging from $25,000 to $40,000. Within the subset of indirect DR systems, there has been a very recent split in the fundamental architecture, with Fuji bringing a major change to the market. Fuji panels are distributed by IDEX and Universal. As discussed earlier, in flat panel detectors there are two main layers. The first is a scintillator layer. This absorbs X-rays and converts them into light. Scintillators are made up of materials like gadox and cesium iodide. The other important layer is the detector layer. These thin film transistors, or TFT layers, are the electronics that make up the pixels that capture the scintillator's light and convert them into an electronic signal. What Fuji has done differently with their irradiation side sampling ISS architecture is to put this detector layer on the front side of the panel, whereas virtually every other flat panel manufacturer places a detector on the back side. To understand the impact of where you put the detector, let's understand the chain of events that leads to a radiograph. Basically, the X-ray comes in and is absorbed within the scintillator. This then converts that X-ray into light. This light is then projected onto the pixels of the detector layer. As the light travels through the scintillator, it sprays and decays slightly in intensity. So the signal will be stronger and better resolved if the detector is as close as possible to the absorption event. For perspective, these layers are on the order of 600 microns thick. That's 0.6 millimeters. So in general, these are minor effects. Still, if the X-ray is absorbed close to the front surface, meaning in the first half thickness of the scintillator, the image quality will be marginally better with a front-placed detector. If, however, the X-ray is absorbed deeper in the scintillator, the detector is better placed on the backside. If an absorption is in the middle third, let's say, it's a wash. So the main question is, where are the X-rays actually absorbed? Well, it turns out that the probability of an absorption event is higher the deeper in the panel you go. In other words, the X-ray is more likely to be absorbed in the bottom half of the detector. And so since more X-rays are absorbed in the bottom half, the best signal quality is measured with a detector on the bottom of the panel. Still, these are hardware differences, don't come from any technological or manufacturing advances. They are just different ways to do the same thing. As such, they account for only minor differences in panel sensitivity. Flat panels in our industry are, as a whole, very sensitive. One other minor point is that when the detector layer is placed on the front side of the panel, X-rays have to pass through this screen, which contains electronics, on their way to get absorbed. So there will be a minor signal loss due to this front side barrier. All of this is very much secondary to the most important step in the acquisition process, image processing. The minor level differences only yield raw image data, which is virtually useless diagnostically. The single most important aspect of image quality is image processing, and the single greatest advantage of sound digital radiography is the implementation of Musica, image processing software. Musica ensures the highest image quality across all contrast layers of an image, as well as consistency across all species, X-ray techniques, and users. To learn more about these benefits, ask your DR specialist about Musica.